Hello, student. Hope you're doing well today. And today we begin the notes in our next topic of study in science class this year. We are progressing through our study in this fourth and final unit in astronomy. And we have been exploring various topics like the electromagnetic spectrum and light and the universe and stars in general. And now it's time to focus in on one star in particular, the one that is the most important star for us here on planet Earth, and that is the star we affectionately call the sun. So we're going to begin talking about the sun today, and that is S-U-N, not S-O-N. So we're going to be talking about the sun today. So join me, if you will, in your books. Make sure you're open to your notes section and you are ready to begin. So as we begin talking about the sun today, I want to put the sun into a little bit of perspective here. Have any of you ever traveled around the entire planet Earth? Probably not many of you, right? The Earth is a big place relative to us. And yet, we're not that big compared to other things, including the sun. Check this picture out here. And in the upper right-hand portion, you can see a little blue dot. That is about the size of the Earth compared to the sun. And this is an actual image of the sun. This is what the sun looks like through certain wavelengths of light. And here is the size of the Earth. In other words, the sun is a big place, and there are some various activities that take place on the sun that are many times larger than our entire planet. So as we learn about the sun today and throughout the week, keep in mind that we're talking about some pretty big stuff. And if you recall our topic from last week with stars, the sun is only a medium-sized star. There are many stars in the universe thousands of times bigger than our own sun. But this week we're only focusing in on our favorite star, the sun. Now, you don't have to copy this all down, but this is a diagram of the internal structure of the sun. And some of you might be asking, how in the world do we know what the inside of the sun looks like? Well, there are various instruments that we can use to peer at different levels of the sun and see different layers of the sun. But a lot of what we know about the structure of the sun comes from scientific experimentation and hypotheses here on Earth. No, we've never taken a sample of the sun because the sun is made of plasma, which is the fourth phase or state of matter, and it has got such high energy, we wouldn't even be able to bring a sample of it back to the Earth. That would just be impossible. But in our books, let us discuss a little bit about what we believe the structure of the sun to be like. So you've got a diagram in your books, and we're going to label it now, and I'm going to start at the top and work my way down. On the very outside of the sun, we have what we call the corona. The corona, as we will learn later, is only visible during a solar eclipse unless you have a telescope equipped with a special device. But the corona is called the corona because corona is a word that means crown. And so the sun has kind of a crown all around it. Again, we're going to talk about these different structures of the sun in more detail in a little while, but right now I just want us to label this diagram. The next one down, and we're working our way into the sun, is the chromosphere. Chromosphere, in fact, chromo is a prefix that means color. The chromosphere, the sphere is a round, three-dimensionally round structures. So chromosphere is like the color sphere of the Earth. Below that, we have the photosphere. And the photosphere, photo refers to light. It's where the visible light comes out. The next one is at the very center of the sun, or any star for that matter, and it is the core. The core is where the nuclear fusion reactions take place, and between the core and the photosphere is the largest part or structure of the sun, and we call that the convection zone. And the convection zone is where that heat energy is transferred or moved from an area where it is most highly concentrated in the core to the surface of the sun outwards. And the temperature generally decreases from here to here. But then funky things happen, as we will discover. So be sure to copy down and label your diagram of the sun. All right, so let's begin with the outside and work our way in. And we're going to begin with the sun's atmosphere. Now, some of you might be thinking of the Earth's atmosphere, and we're familiar with the Earth's atmosphere from earlier in the year, and how there are different layers in Earth's atmosphere, and it's the gaseous part surrounding our planet Earth. But when we think of the sun or a star, we may not really think of an atmosphere. I mean, after all, isn't a star a big ball of burning gas in the first place? No, it is not. A star, as you may recall from last topic, is a supermassive object that is undergoing nuclear fusion reactions. And the state of matter that makes up most of a star, including our sun, is plasma. It's not a gas at all. So our sun, like other stars, is not a burning ball of gas. It is a nuclear fusion reaction taking place, producing plasma, the fourth phase of matter. But be that as it may, on the outside of the sun, we do have three layers. And generally speaking, we call those three layers the photosphere, the chromosphere, and the corona. So let's discuss them from the outside first, beginning with the corona. The corona is the outermost layer of the sun's atmosphere. And as I alluded to earlier, the word corona means crown. Imagine a king or a queen having a crown put around their head. Usually, as you see that crown, if you've ever been to a fast food place, you may have even worn a crown, perhaps. And, crown typically has those little spiker doodles coming around the top, and it signifies royalty. Well, if you think of those little spiker doodles coming up around the outside of the crown, that's kind of what the corona looks like when you see just the corona. During a total solar eclipse, that is really the only time naturally here on Earth you can even see the corona. If you've ever drawn a picture of a star, like, let me just go back to this diagram. We've got these like flame-like structures coming out. Maybe you've drawn a picture like that, or you've drawn a picture of the sun with lines coming out. Those lines are like the corona of the sun. Well, the corona, as I said, is the uppermost layer of the sun, and we can only see it here on Earth during a total solar eclipse. We're going to be talking more about the corona later on. Some weird things happen in the corona. There's a lot of energy being released from the sun, and that energy is released through the corona. The temperature of the corona is unbelievably hot, and again, we'll talk about that later. All right, the next layer of the sun's atmosphere is called the chromosphere. The chromosphere, also known as the middle atmosphere, is an area that really produces the color of the sun that we see, because chromo means color. Now, this is not the best image right here, at least for our sun, but here's the deal. We draw this. What color do we draw the sun? If we've got crayons or markers, what color do we draw the sun? Yellow, right? Yeah, we color the sun yellow. Why? Because our sun is a yellow main sequence star. It produces a lot of yellow light, unless it's sunrise or sunset, and that light is refracted through the Earth's atmosphere, and we see orange and red. But the sun is a yellow star. If you were many million miles away from the sun and you saw it up in the night sky from wherever you might be, it would appear as a yellow star. That yellow color is indicative of the chromosphere. The chromosphere of any star, including our own, is the color portion of the sun's atmosphere that produces the distinctive color that we see. All right, the next layer is called the photosphere. The photosphere, and the prefix photo means light, like photograph means an image produced by light. But the photosphere is, and I put in quotes, the surface of the sun. Now, why do I put the word surface in quotation marks? It's because there is no solid surface of the sun. You couldn't actually walk or land a vehicle on the sun. You would fall straight through. But the surface of the sun, or the photosphere, has a greater density than the chromosphere and the corona. And because it has a greater density, when viewed properly through a telescope, and you should never aim a telescope or binoculars or even your own eye at the sun, because it could burn a hole right through your retina because of the light coming off of the photosphere. There are special things that can be done in order to view the photosphere. And hopefully, if we have a sunny day this week, we'll be exploring looking at the photosphere by projecting an image of the photosphere on a white screen as viewed through a telescope. We never put our eye on the eyepiece lens of a telescope or binoculars aimed at the sun, because you will immediately go blind, and that would not be good. But that image can be projected in various ways, and that projected image, can be viewed. NASA also has special instruments and tools on telescopes, both on Earth as well as in space orbiting the sun, that enable us to view the photosphere, and we can see different things happening on the surface of the sun, various storm activities, which we will talk about in the near future. And these activities we can see on the surface or the photosphere of the sun. But now let's dive into the sun's internal structure. And there are three portions to the sun's internal structure: the core at the very center, the radiation zone, and the convection zone. So let's talk about each of these three, beginning with the convection zone. If you have ever boiled a pot of water, then, to make pasta or rice or something like that, think of the pot on top of the flame or the heating element, and you've got a concentrated heat source down at the bottom of that pot filled with the water. But if you heat it long enough, you know that the water will boil, and the rice or the pasta is going to be spinning around in that boiling water. And the reason for that is something we learned about earlier in the year when we talked about heat, and that is convection. Convection is when energy, in particular heat energy, is transmitted through a substance. Now, here on Earth, that heat energy is typically transferred or moved through a liquid like boiling water or the air in the room or the atmosphere. But on the sun, the convection zone is an area of the sun where heat energy is moving through plasma, and it goes from an area of higher concentration to an area of lower concentration. So it goes from the inside toward the outside where the surface of the sun is. And when we talk about convection currents here on Earth that cause the weather, if you recall learning about weather on Earth, in previous topics, you know that the bigger the difference between the temperature, the bigger the difference there is in air pressure, and the more violent the storms are. But here on Earth, we're talking about really a few degrees. On the sun, we're talking about millions of degrees difference. So, if a few degrees difference can cause violent storms like tornadoes and hurricanes here on Earth, imagine what millions of degrees difference can produce on the sun. Oh, yeah. The sun is 150 million kilometers away from us, and yet storms that are produced on the surface of the sun can affect things here on Earth. And we'll explore that kind of stuff later on. But let's move in a little bit closer to the center as we mentioned the radiation zone. The radiation zone is an area or a zone, a region in the sun where energy is carried by radiation. Now, we've talked a little bit about radiation in the past when we talked about the electromagnetic spectrum. You're going to learn a lot more about radiation when we get into nuclear chemistry in 8th grade. But radiation has to do with things that are happening on a nuclear level. So we've got the basic structure of an atom. An atom, the basic building block of matter, has electrons zooming around the outside, and on the inside, we've got protons and neutrons. Well, those protons and neutrons in the nucleus of an atom, when things start happening there, that's called radiation, basically. And as we are in the radiation zone here, we're not talking about just heat energy. We're talking about energy from changes that take place in the nucleus of atoms, which leads us to the core. Because the core is like the nuclear furnace of a star. It is a place of nuclear fusion. Nuclear fusion is what takes place when you've got the very nuclei of atoms, typically hydrogen atoms, as we've learned before. Hydrogen atoms, the nuclei of those atoms, are being squeezed together because of the incredible gravitational force, because of the massive size of a star, even our own sun. That nuclear fusion takes place, and hydrogen atoms fuse together to form helium. And the way that happens is by changing the nucleus. The nucleus of atoms undergo changes. That releases an enormous amount of energy, which is why the core of our sun is, in fact, the hottest place of our sun. And it's also why the area around the core is called the radiation zone, because that's where those changes are releasing a lot of energy. So, as we think about these basic structures of our sun, we've mentioned a lot of information about the heat and the energy released. So we're going to finish up today by discussing some of the sun temperatures, or in other words, the temperatures of these different regions of the sun. And for this discussion, we're going to start on the inside and work our way out. So let's begin in the core. The core of our sun, which is actually typical of other stars as well, is equal to or greater than 15 million degrees Celsius. Think about that for a moment. That is a big number. It requires that incredible temperature in order for nuclear fusion to take place. The squeezing together of those atoms of hydrogen to form helium. You need temperatures in excess of 15 million degrees Celsius to achieve that. On the sun, it's achieved through the enormous gravitational force because the sun is so much more massive than the Earth. We can replicate or duplicate or produce nuclear fusion here on Earth in the lab, but it takes a lot of energy in order to do that. We are currently working on ways to achieve nuclear fusion here on Earth to provide a clean form of nuclear power. Currently, the nuclear power we use is through a process called fission, where we take big atoms and split them apart. That requires energy too, but not nearly as much energy as fusion. Fusion reactions, like that take place in the sun's core, don't produce any radioactive byproducts like fission do here on Earth. So scientists are feverishly trying to reproduce the core of a star here on Earth. Maybe by the time you're my age, the Earth will have perfected this technique. All right, let's move on out to the photosphere, aka the surface of the sun. Look at that difference. The photosphere drops down markedly to about 6,000 degrees Celsius. Now, don't get me wrong, 6,000 degrees Celsius is still pretty hot. But compared to 15 million degrees, not very hot at all. But it's the photosphere and the temperature of the photosphere that enable a star like our sun to glow a particular color. And when a star glows with a surface temperature of about 6,000 degrees, that glows yellow. That's why our star is a yellow star. But now weird things happen. Weird things happen as you move away from the surface of the sun. Check this out. When you extend up to the chromosphere, the temperature starts increasing again to over 27,000 degrees Celsius. And really, nobody understands why. We have some satellites that we have sent up in recent years to study the sun more closely. We have a satellite up there called SOHO. We've just launched not too long ago the Parker probe, which is studying the chromosphere of the sun as well as the corona. Check this out. The corona, which extends into space, goes up to over 1 million degrees Celsius. Nobody understands why. Logic would dictate that the farther away from the core, the colder the temperatures get, and the temperatures would continue to decrease. So scientists are kind of baffled as to why the corona is so super hot, 1.7 million degrees Celsius. We just don't understand it yet, which is why we are still studying it. Hopefully, your generation will learn the reason why, and perhaps maybe we'll learn something that will benefit us here on Earth. But until that time, it remains a mystery. But as I said before, these extreme temperature changes allow for some pretty nasty activity to take place on the sun. There's activity that occurs on the sun that affects us here on Earth and elsewhere in our solar system. But I'm going to keep you in suspense because those wild and dangerous things, those various forms of solar activity, we're going to start talking about tomorrow. And so for now, I'm going to say bye bye.